Hello everyone. I'm going to make a series of video lectures on complex analysis topic. Though it is a very wider course, but I'll not discuss everything about it. We start with the analytic function, and they are majorly part of the GATE syllabus of these three streams: electric engineering, mechanical and electronic and communication. And we will discuss the one which is the common portion of it. So I'll begin with the today's lecture on analytic functions. And under this video lecture, what I'll cover, first I'll start with that how do we write any complex function into real and imaginary part. This would be the starting of it, and then we will switch to the definition of analytic function, and we'll see the condition which are useful to determine whether the function is analytic or not. And then we have a Cauchy-Riemann equation under it, which is again a very important equations used for checking the behavior of analytic function. And then in the last we have some examples based on it. So let us start with the first one. So we'll see how do we write a complex variable function into real and imaginary. So for that we need a complex variable. Here z is equals to x plus iota y is a complex variable which is an input, and we write a function of that complex variable as a f of z, and we denote it equals to w. And you will observe if input is a complex, the output is also in a complex. So complex variable function mapped from complex to complex. So for that we also express the complex variable function f of z, or you can say w, in terms of real and imaginary part. So we are fixing here u and v for that, u as a real and v as a imaginary. And we will see that how do we rewrite. So when you plug in the z value as x plus iota y, so after simplification, when we rewrite f of z into the real and imaginary part, u is always in x and y, so we call it a real part of fz, and v is also written in x and y, so we call it an imaginary part of f of z. Let us see some examples, or we can say some exercise wherein we will see that how we can rewrite it into u and v part. The first example taken here is f of z is equals to z square. So we want to write down into u and v form. So what we will do, we plug in the value of z is equals to x plus iota y in place of z, and here it is square. So when you apply the whole square formula, after simplification, we get x square minus y square plus 2xy iota. We applied a plus b whole square formula, and you know wherever there is a iota y square, it is minus y square. Why? Because iota square value is minus 1. So from here we jot down what is u and v of the this function. This function u gives us x square minus y square, and y we are getting 2xy. And then let us see one more example quickly, and here it is f of z is equals to mod z square, and you know it is mod z square. So what is mod z value? It is root of real square plus imaginary part square, and since it is a mod square, so root and square will get cancelled, and we only left with x square plus y square. So you can see here it is a real expression. So as we are calling that every function, if you want to write down into real and imaginary part, so how do you locate its real part and what will be its imaginary part? Since there is no I term, so we call it a u 0. So here v value is 0 and u value is x square plus y square. Now we will see the definition of analytic function. So to start with, let us take this one definition, which is at a point. So we call a function fz of a complex variable to be analytic at this point. Means if you are saying there is a point and this point is known as z0, and we are saying that the function is analytic at that point. So what are the requirement? The first requirement is it should be differentiable at that point, plus it should also be differentiable at points in some neighborhood of that point. It means the differentiability is not enough at a single point. The differentiability is also needed with the surrounding point. So you cannot say the function to be differentiable at a single point is also analytic. No, it should also declare that something in the surrounding, it is also differentiable. So if you are having some disk around that point and the function is differentiable within that open disk, then only you can say that it is a analytic. So analyticity about a point means differentiability in some open disk about z0. So this is a where we are calling a analytic behavior at a point. Now when we are having a region, for example if there is a region R and we want to say that the function is analytic within this region everywhere, so what do we need for that? the function should be differentiable at every point. So obviously every point is surrounded by some point, and when we are saying that it is differentiable everywhere, so the every point has a disk, and they are all differentiable. So when you club in everything over here, so it is a differentiability is happening within the whole region. So when it is within the whole region, you can say the function is differentiable at every point of R. Now one point you should remember that analyticity implies a differentiability, but differentiability does not imply that it is analytic or not. Because yes, when function is analytic, what does it mean? It is differentiable at a point as well as in the surrounding. But when we are saying differentiability only at a point, so we don't know whether it is surrounded by, it is not needed, right? For differentiability at a point, only point derivative is needed. But for analyticity, we need two things: point as well as its neighboring point. So if this is okay, it is already included in, but if this is only okay, it is not, you cannot say that it is analytic. So this is important remark, you can say. And we also call analytic function as a holomorphic function. This is also one more name for it. But as you know that we are more interested to see that how do we judge, how do we find out whether the function in front of us are analytic or not, because we cannot think like in a disk form. So we need some important result which are enough for that. So we are going to discuss the first condition, which is a Cauchy-Riemann equation, and this is a necessary condition for any function to be differentiable or analytic. So whenever we have a function, we write u plus iota v, and there are two equations called Cauchy-Riemann equation. What are Cauchy-Riemann equation? That you take u, and it is a real part, and differentiate with respect to x. That u, this small x, means a partial derivative with respect to x. So when you differentiate u with respect to x, the value should exactly equals to the partial differentiation of this v function with respect to y. So ux is equals to vy. This is the first equation. And the second equation is when you differentiate again the u function but with respect to y, and the value should be equals to negative times the v of x. So the first they are equal, the second they are of opposite sign, equal and opposite sign. So these are the two equations. So we can say that these equations will tell us whether the function is necessary condition, because if these conditions are not satisfied, you can declare neither it is differentiable nor it is analytic. So remember, if the function does not satisfy CR equations at a point, it is not differentiable and hence not analytic at that point. So this is a necessary condition, that it is needed. Now we want to talk about that when do you say that it is analytic. So what is a sufficient condition which will useful to find the behavior of the function, that it is analytic or not, or a holomorphic or not. So the first one is the necessary one, which is needed, that the function should satisfy CR equations. Plus we need one more condition. What is that? If we can see that these four partial derivative which we are using here for the CR equation, they are all continuous. So if they are continuous along with CR equation satisfied, we can say that the this function is analytic. Now see, you cannot say that by only continuity checking is enough. No, this necessary condition plus if you add on one more condition, that is they are all continuous, we can say yes, the CR this function is analytic function. Now let us see some examples. I'll start with the, we have a 2-3 examples over here. Let us see quickly. The first example I have taken here is show that the function fz is equals to z square is analytic everywhere. So everywhere means whole complex plane we are talking about. So what we will do, we have to follow those two conditions which are sufficient. So first we need to express the given function into real and imaginary part. So we have already discussed in the starting how to write z square into real and imaginary part. So we figure out what is u and v for it, and then the first condition checking. Let us see that whether CR conditions are not satisfied, because if the first condition fail, we are not interested in the second one because it is the necessary. So first is you take ux, which is equals to 2x, and here u is there, so when you partial differentiate you get a 2x here, and uy is equals to minus 2y, vx is 2y, and Vy is 2x. So we see that these two are equal. So Ux is equals to Vy. The first condition is satisfied. Second condition, equal and opposite in sign. Yes, it is also equal and opposite in sign. So CR equations are satisfied. Now the second condition is, because first set necessary condition is done, second condition we will check that whether all ux, uy, vx, vy are continuous. Yes, all are polynomial, and we know that polynomial are continuous everywhere. So here the second condition is also done. So we do not have to prove it, we can see the function and use its basic nature. So polynomial continuous everywhere. So two conditions satisfied for all x and y. There is no point where it is having a problem. So we can say that this function is analytic everywhere. Now the second example is the good one, which pay attention for that. Here we are having a mod z square as a function, and we want to show that it is not analytic at any point. So we do the same thing. We calculated this ux and u and v value. U is x square plus y square and v is 0. After doing the partial derivative, for partial derivative is already done here. 2x for u and uy is 2y, and then we see 0. Now from here we will first see the necessary condition is not satisfied here. Why? Because you can see that it is a variable x and y, and you cannot say 2x is always equals to 0 and 2y is always equals to 0, negative of 0. Then CR equation very easily visible, it is not equal for all x and y. Let us find out, are there any points where they are equal? So when you equate these two equations, first equation you are equating, and we got that the first CR equation has given x value to be 0. When I applied the second CR equation, that if this is equal, we got y 0. So from here I have gotten that CR equation only satisfied at one point. So that point is an origin. So from here we can declare one thing, that the function is differentiable, but the function is not analytic. Reason being, the only one point CR equation satisfaction means it is differentiable. There is no information, there is no nothing is about the other points. So when there is no other point, you can say that it is failed to be analytic. And it is the best example for my second, that one we say na, differentiability applies analyticity apply differentiability, but differentiability always not apply that it is analytic. So here we got that result. So we can say only one point is considered, that it is differentiable at origin. That's it. Now we will see one example, last one, that x minus iota y whole square, and we want to see that is there any point or where, if anywhere, it is function is analytic. So let us quickly find out its u and v. I have already simplified that when you apply the whole square formula, because negative it will be minus 2xy. So we got uv. So when we differentiate u with respect to x, we get 2x, uy it is minus 2y, vx is minus 2y, and vy is equals to minus 2x. Now you can easily see that. How do we check? We first check that these two should be equal. But you are observing they are not equal. Why? Because 2x is not equals to minus 2x, and 2y is also not equals to negative of 2y. They are same. So these conditions are not equal. So CR equations are not satisfied. So we can conclude that the function is not differentiable at any point, and hence it is not analytic, because we have already shared that in the necessary condition, if the function fz does not satisfy CR equation at a point, it is not differentiable and hence not analytic at that point. So this is one of the example. This example number this second one, which we have seen, this second one, this second example was giving us information about this remark. The remark was saying analyticity implies differentiability but not vice versa. So we have seen here that in the last example, we have, in this first example, everywhere it was satisfying because both the condition were fulfilling. Second example, we have seen that only one point it is satisfying, so CR equation satisfied at a point will give us only differentiability at that point. And in the last example, we have seen there was none of the point where, not even a single point where CR equation was satisfied. So we got that it is not differentiable. If it is not differentiable, so there is no question of analyticity, because differentiability is first differentiability is needed, then only you can switch to the analytic function. So I hope you have understood. Thank you.